Okay, so this lecture covers this concept of Gibbs free energy, given this symbol G, or change in free energy, given this symbol delta G. And so delta G is equal to the change in enthalpy minus the temperature times the change in entropy. Okay, so if delta H minus T delta S is greater than 0, so if delta G is greater than 0, so if delta G is positive, then the reaction is non-spontaneous. So under what circumstances will that happen? So if enthalpy is positive, so if it's endothermic reaction, and if delta S is negative, then this entire term becomes positive, and so under all situations, no matter what the temperature is, delta G would be positive and the reaction would be non-spontaneous. If delta H is positive and delta S is positive, so if delta H is positive, if delta S is positive, then the reaction could have a delta G positive or negative. That depends on what the temperature is, right? So if the temperature is low, so if T is low, then the T delta S term is small and the delta H term predominates. So at low temperature, in this situation, the reaction delta G would be positive and it would be non-spontaneous. But if temperature is high, then the T delta S term predominates, and then delta G would be negative in that case. So at high temperature, then the reaction would be spontaneous. Or if T delta, so under what circumstances can delta H minus T delta S be less than 0? Well, so if delta H is negative, so if it's exothermic, and if delta S is positive, so if it's positive entropy, so it goes to more disorder, then T delta S term will always be negative. If delta S is positive, so under all, no matter what the temperature is, delta G would be negative. So if it's exothermic and it has goes toward disorder, so entropy is positive, it will always be negative, so that will always be a spontaneous reaction. Okay, or you could have a situation where it could be positive, delta G could be positive or negative depending on what the temperature is. So if delta H is negative, so if it's exothermic, and delta S is negative, so it goes towards more order. Then if T is low, then enthalpy would predominate, delta H term would predominate, so in this case delta G would be negative. So at low temperature it would be spontaneous, and at high temperature the T delta S term would predominate. And if delta S was negative, the negative T delta S term would become positive, and so at high temperature then delta G would become positive, and that temperature, and then that reaction would be non-spontaneous in that case. So if delta H minus T delta S equals 0, what does that mean? So that means delta G is equal to 0, and that means you're at equilibrium. So again, so one of the purposes of determining delta G is to know, first of all, is the reaction going to be spontaneous or not? If delta G is less than 0, it's spontaneous. If it's positive, then it's non-spontaneous. And it also tells you how efficient that reaction is, whether it's high yielding or low yielding. And we'll talk about that in a little bit more later. So let's take an example. So if we take this reaction, ammonia gas plus CO2 gas to make urea plus water, liquid. So if delta S for this reaction so is given, so if delta S is, so if delta S is negative 356 joules per Kelvin, and delta H is negative 119.7 kilojoules, and this is at 25 degrees Celsius, Oh, there it is. Then what is delta G? So we can just plug into that equation. So delta G is equal to negative 119.7 kilojoules minus, so temperature is in Celsius, you need to convert that to Kelvin, so that will be 298 Kelvin. And then, so delta S is in joules per Kelvin, and we need to convert that to kilojoules since enthalpy is in kilojoules, so that would be 0.356 kilojoules per Kelvin. And if you multiply that out, delta G is equal to negative 13.6 kilojoules. So it's negative, so it's spontaneous. Okay, so let's take another example. So this is example 18.4 from your textbook. So if you take CH4 gas, 2 oxygen molecules to make CO2 gas, and 2 water molecules in the gaseous state. So let's calculate what is delta G for this reaction. So we need to look up delta H values and delta S values, so we need to use appendix C from your textbook. So delta H for CH4 is negative 74.87, and water, heat of formation of any element and its most elemental state is 0. CO2 is negative 393.5, and water is negative 241.8, and all of these are kilojoules per mole. And so again, you have to pay attention to the state. You have to make sure you look up H2O gas and not H2O liquid. Same for all of these. CO2 solid or CO2 liquid or CO2 gas. You got to pay attention to the state when you look these numbers up in the table. And then delta S values, 186.1 for ammonia, or for CH4, 205 for oxygen, 213.7 for CO2, and 188.7 for water in the gaseous state, and all of these are in joules per mole Kelvin. Okay, so we can calculate delta H0, right? Summation of products minus summation of reactants, and then do the same thing for delta S. So delta H is equal to negative 393.5, so for the CO2, plus, so there's 2 water molecules, so you have to make sure that you multiply these numbers by 2 when you do the math. Okay, so that's the products, and then subtract off the reactants. And again, there's 2 oxygen molecules, so you have to multiply these numbers by 2. Okay, so if you calculate that out, delta H is equal to negative 802.23 kilojoules. And then do the same thing for delta S. So take your products, so 213.7 for CO2, plus 188.7 for H2O, and you have to multiply that times 2. And then subtract off the reactants, 186.1 minus 2 times 205. So delta S is equal to negative 5 joules per mole Kelvin. Okay, so if you notice, delta S is very small, which is around 0, and you could predict that just from the reaction because you have 3 gas molecules on the left, go to 3 gas molecules, CO2 and 2 waters. So 3 gases become 3 gases, so there's not much change in order, so entropy should be around 0. Okay, so now we can calculate delta G is equal to delta H minus T delta S. So just plug in the values, negative 802.23 kilojoules minus 298 Kelvin. And again, so this is in joules, so we need to convert that to kilojoules since the enthalpy is in kilojoules. So delta G is equal to negative 800.7 kilojoules, which is less than 0, so it's spontaneous. Okay, so it can also calculate delta G. So you can also calculate delta G another way, a much more simple way using this formula. So delta G is equal to summation so just like delta H and delta S, you can sum. There's thermodynamic values for delta G in the appendix as well for each of these different compounds. So you can look up the delta G values for the products, sum them up, sum the delta G0 for the reactants, and subtract the two. So if we look these values up in the table, for CH4 it's negative 50.8 O2, so delta G0 formation of any element is 0, and so CO2 is negative 394.4, and H2O gas. Okay, and delta G for water gas is negative 228.6, and these are all kilojoules per mole values. Okay, so now we can come down and plug it into this equation. Delta G is equal to the summation of delta G's of the products minus delta G's of the reactants. So delta G for this reaction is negative 394.4 plus 2 times negative 228.6 for the oxygen. So that's yeah, that's for the products. So for the CO2 in the water, and then sum the reactants. So negative 50.8 plus plus 2 for the O2 times 0. So delta G for the reaction is equal to negative 800.8 kilojoules. And so of course you should get the same answer as you got using the T delta H minus T delta S equation. Okay, so if delta G is large and negative, so if delta G is around negative 10 kilojoules or more, then it's spontaneous, and the reaction goes in around 100% yield. If delta G is large and positive, so if it's around positive 10 kilojoules or more, then it's non-spontaneous, and the yield is very low. So it's almost all reactants and almost no products. Whoa. So if delta G is somewhere between about negative 10 kilojoules and positive 10 kilojoules, then that means you're going to have an equilibrium mixture, so you're going to have a substantial amount of both reactants and products. Okay.